right, so last class we proved the first part of Gauss Markov Theorem. We showed that beta hat is an unbiased estimator for beta. And now we're going to show that it's the best estimator, meaning it has minimum variance. So, as a recap, Gauss Markov Theorem, this says that least squares is the best linear unbiased estimator, or BLUE, sometimes as an abbreviation. What does this mean? Well, it means it's best in that it has the smallest variance. It's linear in that it's linear in the observed output variables. It's unbiased. We showed that last time because the expectation of beta hat is equal to beta. And it's an estimator. We also know that that's true. So let's prove that first part, the best part now. So what do we need to do? Well, first we need to come up with another linear unbiased estimator of beta. So I'm going to call this beta tilde. And then we need to show that this estimator has a variance that is no smaller than the variance of beta hat given x. So what is the variance of beta hat given x? Well, if you don't remember, you can go back to the previous lecture. Go ahead and pause this and rewatch that one. I'll give you a second in case you'd like to do that. Okay, so hopefully you reminded yourself the variance of beta hat given x is, because we're going to use that as we move through this proof. Okay, so the first part is to define a linear unbiased estimator of beta. And as I mentioned, I'm going to call this beta tilde. So beta tilde is going to be equal to some matrix C times y. Why CY? Well, this is what we mean by linear. And so C is going to be defined as x transpose x inverse x transpose plus D, where D is some non-zero matrix. So when would beta tilde be unbiased? So what we need to do is show that the expectation of CY given x, and remember that CY is our beta tilde, so we want to show that the expectation of CY given x is equal to beta in order to show that beta tilde is unbiased. And so we can do this similar to how we did with beta hat. We can plug in our definition of CY, our definition of beta tilde. And so that's what this is right here. It's x transpose x inverse, x transpose plus D. And then y, we can plug in our definition of y, x beta plus epsilon. And we're taking that expectation given x. And so go ahead and try this. Go ahead and solve for the expectation of CY given x. And I want you to do this in the application exercise so that you can go ahead and submit that at the end of this lecture. So spend a couple minutes deriving that. Go ahead and you can derive it on paper first and then type it up in your RMD file, or you can just derive it directly in your RMD file. Either way is fine. Okay, so I'm going to go ahead and give you the final answer that you should get to, but make sure that you show all the steps in between for your application exercise. And so beta tilde is equal to dx times beta plus beta. And so what we need is for this expectation to be equal to beta. And so for beta tilde to be unbiased, that means that dx here must be equal to 0. That's going to be the only way that this beta tilde can be unbiased, because basically we need to get rid of this first part. So we're going to make that part of our definition that this is our definition for cy. This is our linear estimator, and in order for it to be unbiased, dx must be equal to 0. This is going to be important for when we're deriving the variance. Okay, so for our estimate beta hat to be best, what needs to be true? We need the variance of beta hat given x to be less than the variance of beta tilde given x, or at least less than or equal to. So basically we need this to be the smallest variance, the variance of beta hat given x, the variance of our least squares estimator. We want that to be as the smallest possible among the class of linear unbiased estimators. So we know that the variance of beta tilde given x is equal to the variance of cy given x, because we know that by definition, beta tilde is equal to cy. So what here is constant? So what I want you to do is go ahead and finish solving for this variance of cy given x. I've given you the first hint that c is constant. So I've pulled c out here on either side. So we have a c and a c transpose. And so you're going to go ahead and plug in for the variance of y given x, which we should know from the previous lecture, and then also plug in our value for c and solve this out. And remember that dx equals 0 for this to be unbiased. So I'm going to give you 3 minutes to work on this. And go ahead and add this to the same application exercise. So the one you turn in is going to have 2 pieces in it. The first being the piece that you solved in the previous exercise, and the second being this piece. Okay, so here's where you should end up. The variance of beta hat is equal to, or the variance of beta tilde given x is equal to the variance of beta hat plus sigma squared times d transpose. And so d times d transpose, this is a positive semi-definite matrix. And so therefore, the variance of beta hat is always going to be less than the variance of beta tilde. And so now we've shown it, this variance of beta hat is best. And in fact, that means that our estimator here, our least squares estimator, is best. And so we've completed our Gauss Markov theorem.